my brand new Lambo.
The object you're looking at is called a Galton board. When it is flipped over, the beads fall out of the reservoir from the top down into the base collectors on the bottom. The distribution of the beads across each collector can be modeled by what is called a normal distribution. Normally distributed data follow what is called a bell-shaped curve, or a bell curve, that has a single peak, which is where the mean of the data set is located. Because the distribution is symmetric, roughly 50% of the data falls below the mean, and 50% of the data falls above the mean. This normal curve has some other interesting facets to it that we're going to examine in greater depth. The x-axis of a normal distribution represents the z-score, or the number of standard deviations a given observation falls from the mean. So an observation which is at the mean would be 0 standard deviations away, represents the center of the data set. That's 0 is the average or mean value. A value of 1 would represent a z-score of 1 is 1 standard deviation above the mean. 2 is similarly 2 standard deviations above the mean, and negative 1.5 is 1.5 standard deviations below the mean. We can use this curve to estimate the percentage of data that falls between a given range of values by calculating the area under the curve. So say I wanted to know what percent of observations falls within 1 standard deviation of the mean. I could look at my normal curve. Within 1 standard deviation of the mean would be between negative 1 and 1 on this curve. So that's between this value and this value. So if I add up all of the values in the area under this curve, I'll be adding up the 15, the 19.1, the 19.1, and the 15, the sum of which would give me around 68. So 68% of the data I expect to fall within 1 standard deviation of the mean. If I repeat this process for 2 standard deviations, the percent of values between negative 2 and 2 on this normal curve, I can simply add up all of these percentage values, and I will find that in this area underneath the curve here, adding up the 19, the 15, the 9.2, and the 4.4, plus the other 19, 15, 9.2, and 4.4, I get about 95% of the data. If I do a similar calculation for everything within 3 standard deviations of the mean, I will wind up with about 99.9% of the data. This breakdown gives me a means by which to evaluate whether or not a data set is distributed normally. We call this observation of 68, 95, 99 the empirical rule for normally distributed data. If a data set is normally distributed, it should closely be approximated by this empirical rule. Using the generalized normal curve, we can also make approximations and inferences about the data if we know that it is normally distributed. For example, suppose that all heights of girls at Friends Academy are normally distributed with a mean of 66 inches and a standard deviation of 1.5 inches. If Kelly is 69 inches tall, we can use the normal curve to approximate her percentile rank of her height. So if Kelly is 69 inches tall, in order to use this normal curve, I'm going to need to calculate her z-score. Using the z-score formula, 69 minus the mean of 66 over the standard deviation tells me that Kelly is 2 standard deviations above the mean. So if I go to 2 standard deviations above the mean, the percentile rank is the percentage of individuals who fall below that given observation. So I would need to sum up all of the observations, or find the area under the curve, for all of the values below Kelly's z-score of 2. Alternatively, I could sum up the values that are above 2 and subtract that from 100. So if I add up 1.7, 0.5, and 0.1, I will get about 2.3%. and I could do 100 minus the 2.3, which will give me approximately 97%. So Kelly's height of 69 inches tall is 2 standard deviations above the average, which puts her in the 97th percentile for girls at Friends Academy. Before we can use a normal distribution, we either have to know that a data set is normally distributed, or we have to check whether or not it's reasonable to assume that it is. To determine if a distribution is normally distributed, that's when we revisit the empirical rule. So, if we take a look at the following, say I wanted to determine what percentage of students scores within 1 standard deviation of the mean. Given this data set, I would first need to calculate the mean and the standard deviation, and then look at the bounds to see what falls within 1 standard deviation. To do that, I will go to my calculator, click on the statistics editor, enter edit, and enter the data set as it appears. So we'll enter my 20 values into list 1. Once those values are entered, I will quit, return to the statistics menu, press the right arrow over to calculate, and I will calculate one variable statistics. Here I have my data typed into list 1. I have no frequencies list, so all I need to do is calculate. So now I know that the mean is 79.7 and the standard deviation is 8.9. So to obtain what's within 1 standard deviation of that value, I will need to look 8.9 units below this mean and 8.9 units above this mean. To calculate that lower and upper bound, I will utilize these statistical variables, which can be found in the VARs menu, under the statistics option, and I will do x bar, which is option 2, minus the standard deviation, which is also stored under the variables menu, under the statistics option. Standard deviation is selection 3. So here I have mean minus the standard deviation, which will give me 70.8. I will do the same calculation for above by revisiting the entry and modifying that subtraction to an addition. So now I have both 1 standard deviation below and 1 standard deviation above the mean. So with a mean of 79.7 and a standard deviation of 8.9, all the values that fall within 1 standard deviation of the mean must be between 70.8 and 88.6. To revisit, I actually want to calculate the percentage of students who scored within 1 standard deviation of the mean. So to do that, I will go through and mark off any value which is not within this bound. So 70 is too small, 60 is too small, 75 does fall within that range, 68 is too small, 85 is fine, 86 is fine, 78, 72, and so on as I count through, counting up each of the values that fall in this range. 74, 79, 86, 82, 90 is too large, 92 is too large, 93 is too large, and 73 is just fine. So I wind up with 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14 out of my 20 observations. My 20 total data points, which is equivalent to 70% of the data. So 70% of students scored within 1 standard deviation of the mean. If I really wanted to know whether or not it would be appropriate to use a normal curve, I would also need to examine exactly what percentage falls within 1 standard deviation, 2 standard deviations, and 3 standard deviations. So within 1, we've already established 70. If I repeat that process for 2 and 3, I will wind up with 95% and 100% of the data. Because 75, 95, and 100 is very close to the empirical rule of 68, 95, 99, it would be fair to approximate these data using a normal curve. Sometimes we also want to calculate values with a normal distribution, but the normal curve itself sometimes doesn't provide a precise enough measure. So in those cases, we can actually utilize the calculator for some normal calculations. So say I have a normal distribution of weights where the mean weight is 160 pounds and the weight of a 186-pound individual has a z-score of 2. I can use this data to calculate the standard deviation of the actual data set. I can do that using the z-score formula. by plugging in each of my corresponding values. I'm trying to find the standard deviation. I have the z-score of 2. My observation was 186 and the mean was 160. And if I solve this for standard deviation, I will get that the standard deviation of this data set is 13. So then say I wanted to know what percentage of weights is between 155 and 165. Well, I can calculate the z-score for 155 and 165, and I get 5/13 and negative 5/13. Now those values don't appear on the normal curve in a very precise manner. So because it's going to be hard to use that normal curve, I'm going to rely on a calculator to calculate this value. So for reference, here is a series of calculations that you can perform on the. If I want to calculate the percent of individuals without having to manually count them on that normal curve, I could obtain that by following the following keystrokes. So I'm going to hit the second key. The variables button will pull up all of my distributions. I'm going to press the down arrow to highlight the normal CDF, and I will press enter. It will then ask me for a series of values. So for here, I will clear whatever's there. The lower value is the lower or smaller z-score that you're calculating. In my case is negative 5/13. The upper is the upper z-value, in this case positive 5/13. And then I can scroll down and click the paste option. Once that is done, I will hit enter, and it will calculate the overall percentage. So it looks like approximately 30% of the data should fall between 155 and 165. So this would give me a result of 30%. Let's try another one. Scroll my reference down. So say I wanted to know what percent are between 173 and 179.5. Well, the procedure is very much the same. I will calculate the z-scores for each of those values. The z-score for 173 is 1 because it falls 13 units above the mean of 160. And 179.5 is 19.5 over 13. So if I repeat the same calculation, I will hit second, distribution, scroll down to CDF, highlight, and enter my lower z-score and my upper z-score. Enter, 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 and paste. Hit enter, and it appears that approximately 9.2% of the data appears to fall within this bound. One final example for normal distributions in this video. Suppose on a standardized test, test scores were normally distributed around a mean of 60 and a standard deviation of 6. Suppose you want to calculate the z-score for 48. Well, from what we've seen, we can just use the z-score formula, and that falls about -2 standard deviations below the mean. If 2,000 students took this test, how many would you expect to score at or below 48? Well, there's two ways we can do this. We can either use the normal curve, as we've seen before. Bring that over to this example. If I use this normal curve, I can look at where the z-score that we calculated, -2, falls in this distribution. It seems to fall here, so I'd expect this percentage, this area over here, to fall below. I can calculate that by adding up each of the individual values. So I have 0.1 plus 0.5 plus 1.7 gives me about 2.3% of the individuals. We could get a more precise version of that using the calculator by again pulling up the normal distribution. But now I have an upper bound, which is -2, but I have no lower bound. So that's a problem when I'm going to plug values in. So what I'm going to do, because technically I want to go infinitely to the left, is just plug in a really large negative value. Then I will plug in my -2 as my other bound, paste it, and calculate it, and notice that it does wind up to be 2.3%, the same percentage that we approximated using that curve. So whichever method you decide to do, that's 2.3% of the data falls below the z-score of -2. And once you have that percentage, 2.3% of the 2,000 students would result in 46 students scoring at or below 48 on this exam. You can also use the normal curve in reverse. So suppose of the same set of data, I was curious what score is going to put me at the 84th percentile. So now I have the percentage, but I want the actual value. Well, I can use the normal curve to obtain a z-value, the z-score, that would get me 84% by adding all of these values up until I get to 84. Now, halfway through the data should be 50, so then plus 19 would give me 69, plus 15 is about 84%. So if I'm in the 84th percentile, 84% of my data should be below this value, which corresponds to a z-score of 1. So if I'm in the 84th percentile of normally distributed data, my z-value should be 1. Well, if that's the z-value and I'm interested in the actual score, I could use the z-score formula and say that 1 is equal to my unknown score on this test minus the mean divided by the standard deviation. And then I can solve this for x. And I would get that x would be a score of 66, one standard deviation above the mean. So a score of 66 would put me in the 84th percentile for this data. Now that's well and good when the values on this curve add up to nice values, but if I want 20% and I start totaling up, it gets a little bit trickier to find exactly where I am. So that's where I return to my calculator. Now we can actually use the calculator to calculate this value as well. I'm just going to bring this to the front. So using these calculations, we can use the calculator to calculate this rather than the curve. So it's similar to the keystrokes for pulling up the normal CDF. I'm going to go to second distributions, but now I'm going to scroll down to inverse norm. And what inverse norm does, if you press the plus sign, it will tell you what the inputs it takes. So it takes the area, the mean, and the standard deviation of the data set. So when I pull up inverse norm, it'll ask me for the area. The area is the percentage under the curve. In this case is 20, or 0.2, 20%. The mean of this data we have is 60, and the standard deviation of this data we have as 6. So then I'm just going to go over here and click paste and hit enter, and it will tell me exactly what score on the test I would need to have scored in that percentile. So I would need a 54.95, which I'm going to go ahead and round to 55. For the 50th percentile, well, that one's kind of easy. We could use either method, but remember that the 50th percentile, since this distribution is symmetric, the data is divided equally in half. So the 50th percentile should put me right in the middle of this graph or at the average. So I'd expect that my score would be what the average is, which is 60. And if we check that using the calculator method, I can pull up the distributions, go down to the inverse formula, an area of 0.5, with a mean of 60 and a standard deviation of 6. If I click paste, I'd expect to get 60 as my observation, and I do. So these are means by which you can do normal calculations using both the curve and the calculator.